equations we have. M is a Hermitian matrix, so therefore it must be of the form, the diagonals are all real, these are all real, right, because Hermitian, and the dagger, since it's Hermitian, it means that if I have a complex number here, let's say Z1, then here it should be Z1 bar, right? If you here Z2, Z2 bar, and so on. And here these are real numbers. Let's call it X1, X2, etc. No? So now we want to set these guys to identity, which means all these guys are set to be 0, right? And all these should be 1. So we have n equations from here by setting all of these guys equal to 1. So the n real equations from the diagonal and real equations from by looking at the diagonal part of this equation from the diagonal. Okay. And this many, how many of them are there? N times n minus 1 by 2, right? That many complex equations, because each of them is a complex number. And when we set that to 0, that means both its real and imaginary parts are 0, right? So we have this many complex equations, which of course means n times n minus 1 real equations. Okay, so altogether we have this plus that many number of real equations, which is in fact, so this implies n plus n times n minus 1, which is equal to n square real equations. Okay. We started with the 2n square real equations, real parameters, and we have n square equations. So those will remove n square of these parameters. And so what will be left over? So the dimension of, or the number of parameters in a unitary matrix. Any matrix which satisfies this condition is called unitary. So this unitary matrix is n square, is equal to 2n square total, the parameters you started with, and n I have to subtract from that the number of conditions I have, n square real conditions. So we have n square parameters. And finally, there is one parameter is removed by determinant of g equal to 1. You see, for generic such choices of n square parameters, we will get something where theta is not equal to 0. No, I mean this will be not equal to 1. But when you set that equal to 1, you remove one parameter also. That is left. You are left with n square minus 1 parameters. And your question about, so I think if I understand your question is that, is it really a smooth space? No? But that you can see, but because if I just choose any particular g, which satisfies this condition. Okay. Now you want to ask, can I change the parameters continuously, right? And that is possible because you can just multiply that g with this exponential of the Lie algebra. If you take g, g has it's some particular unitary matrix with a determinant equal to 1. Now I can multiply to this any parameter which is, let's say, I epsilon a lambda a. Lambda a are those, say, Lie algebra generators. And look at for small epsilon, it will just define to you a neighborhood, no? A neighborhood of that particular point. So this way, you see the space will be, you can define a space, a smooth continuous space. So, yeah.
It seems that the parameterization equations are hard to solve in this case, but does it look like an S8
No.
or something?
No, not at all. In fact, I think there is no other. S3 is the only exception. S3 and of course S1. S1 is the U1. U1 is a circle, right? S1. Apart from that, there is no other sphere which is a group.
We showed last time that inside the hierarchical two algebras.
Yeah.
So if we restrict to
That's
those
right.
spaces, those are S3s.
Exactly.
The bigger space is some kind of a strange combination of 3 S3s.
Well, 3s3s would be like 9-dimensional, so it's kind of a lot of overlaps here. I mean, it's not,
Overlapping them.
yeah, yeah. So altogether it's 8-dimensional.
8-dimensional, something which is composed of S3 slices.
Yeah, sort of, yeah. Because I mean, so how will I get S3? So if I look at this 3x3 matrix and set one of them equal to 1, and 0, 0, 0, 0, and here of course I will have an SU2 then. It will be just Z1, Z2, what was it? Z2 bar or minus Z2 bar, and Z1 bar, something like that, right? That was the. So this will be certainly contained inside SU3, and this will be a S3. But then you have set this equal to 1, right?
But they are overlapping and you can go any point using these sub-algebra parameters. So
Sure,
you can
yeah.
somehow, in 3 steps, go everywhere on the strange thing.
Yeah, it's a strange thing, but I think it's not so easy to write it as, you know, I mean, once you start turning on everything, I mean, this way is an there's an S3 here, right? Similarly, I could have put the 1 here and these guys, no, and so on. So there are 3 S3 subgroups are there, right? But once you turn on everything, it becomes very difficult to even see where is S3, no? Yeah.
But this space also is bounded. In the
Sorry?
SU3. It's
Sorry?
also bounded? In
Yeah, yeah,
SU3?
it's all bounded, yeah, yeah. That's right.
How do we know that?
How do we know that?
Yeah, so what? We can prove for SU3 there is also a bounded.
Well, you can, let me see, maybe, I don't know, for example, let's see, just take any row, for example. So let me just look at this structure here, Z1, Z2, Z3, up to Zn, right? And then similarly, every row. I mean, but let's focus on this row. And let's take the dagger of this. So I'll get Z1 bar, Z2 bar, Zn bar, yeah? And so on, and the other things. I'm just focusing on one row and one column. Okay. Now, when I multiply this, the answer should be equal to 1, right? I mean that particular thing.
Yeah.
But that already tells me that Z1 mod square plus Z2 mod square plus, so this is all equal to 1. No? So every vector, I mean like this vector, the next vector, all of them have to be bounded. No? So it will be compact space here. I mean, of course, if you change the sign, if you like what we were doing, I mean, if this is because it's 1. Suppose it was an indefinite signature. Some of them are plus sign, other are minus sign.
Like it.
Yeah, then it will be a mess, like eta or something. No? Then it will be a mess because some of them will be negative. So the whole thing will be will not make sense. No, it will not be. It will be something like more like eta eta. This will be the analog. But still, I mean, you'll find that the resulting space will become non-compact. If there are some, not all of them positive. If there are some signs positive, some negative, then yeah. Okay. Anything else? Any other question? Okay, so if there are no other questions, any question? No? Okay, then let's continue with what we were doing. So we had those bases, let me just write it down somewhere here. Professor. I mean, it's already, okay, let me not write. Sorry. Okay. Yeah, you have, all of you have the notes in front of you, right? So that I don't have to write those 8 matrices. It will occupy all the blackboard. Yeah. So and then so let's just here. So we said just like what we did for the SU2, when we took the combination sigma 1 plus I sigma 2 or sigma 1 minus I sigma 2 to get the eigenstates. And when we did sigma 1 plus I sigma 2, it just became an upper triangular matrix. Sigma 1 minus I sigma 2 is a lower triangular matrix. So in the same way, we can write now so first of all, the diagonal ones give you the kappa. Diagonal matrices give you the kappa subalgebra. That's only two-dimensional because the trace condition. Because the trace has to be 0, so there are not 3. Because it's a 3 by 3 matrix, so there are 3 diagonal elements. So you would imagine it's a 3-dimensional space, but because we have tracelessness condition, there are only 2 independent. And we can call, let's say, H1, we just defined as 1 minus 1, 0, diagonal, everything else 0 there. And say H2, defined 0, 1 minus 1, everything else 0. Right? Clearly, any matrix, any traceless diagonal matrix, I can write it as some AH1 plus BH2. Right? So therefore, this is a basis. Okay? Right? Because if you do that, then this will become A minus A, B minus B, and then add it up, so you will get here A minus A plus B minus B, and indeed the trace is 0, of course, because individual traces were 0. So that's the diagonal part. So this gives you the kappa subalgebra. And then you have the remaining guys. Remaining guys we split into these combinations, which are upper triangular or lower triangular. So this one, it was 0, 0, 0, 1, 0, and everything else 0. X alpha 2 was 0, 0, 1, and then everything else 0 here. And X alpha 3 was 0, 0, 0, 1, 0, 0, 0, 0, 0. And X minus alphas. Alpha 1, I just take alpha I, let's say, which is simply the transpose. X alpha I, X alpha I, transpose. Okay? I mean transpose. So that means this will come here, right? And that will go there, and this will go there. Yeah.
Is there a particular reason for them to be upper triangular or lower triangular?
Well, I mean, I'm anticipating. No, I mean, of course, any of a non-diagonal guy I can expand in this basis. Yeah, I mean, after all, this is what we are calling EIJ, right? EIJ when I is not equal to j. So remember the definition of EIJ. So EIJ was an n by n matrix whose the only non-zero element is the one which appears at the ith row and jth column. Okay. So this was just to, because sometimes it's hard to when you see this IJ, you think that it is a row and column. No, of course in a way it is, but what I mean by this is this whole thing is a matrix. It's not a IJ element of a matrix. The whole thing is a matrix. So EIJ is a matrix which has a property that if you look at the ith row and the jth column, then this element is equal to 1 and everything else is 0. Everything else is 0. Just only non-zero element is that. Huh? So another way to say is that, well, EIJ is a matrix, right? So I have to specify its the row and the column, say KN, kth row and lth column. So I want to specify the matrix, I need to specify all of these numbers, right? And the number here is simply delta IK, delta JI. Okay. That's what. Anyway, so in this notation, all the off diagonal guys are simply I not equal to j, right? So I can just write down any off diagonal matrix, any off diagonal matrix. Of diagonal matrix as equal to some numbers xij, eij, some lower ij with I not equal to j. Right? So this is a basis. It's certainly a basis. So I choose this basis. The advantage with this choice of basis is that these are in fact eigenstates. Okay. So let me just. I think I started saying this, but. So what does it mean, eigenstates? What we want is that the eigenstates are like this. This is the equation. H, any H. H is in general a combination AH1 plus BH2, right? So this is any H in the Cartan subalgebra, right? Right? I mean, this was the basis, but Cartan subalgebra is any element of this form. So this is the Cartan subalgebra. I mean, this is the element of the Cartan subalgebra. So I want to find some combinations such that this is some number. That number will of course depend on H, which H we are looking at. So I call this number, it's a function of H times X. So we want to solve for this equation. Right? So now the claim is that this, if you choose this base matrices, these are in fact eigenfunctions. Eigenstates of that. Let's just check that explicitly. Okay. I will come back to this equation a bit in a little very soon. So these are called the roots. These are called roots. And if you look at this, okay, maybe let me first discuss this kind of abstractly. What is it? Now, of course, this will depend. So what is this alpha? Maybe I should put here an index alpha. So this is the eigenstate with the eigenvalue alpha h. Of course, if it's a different function, it will be different, right? Different eigenstate. So this labeling is like that. So I have some eigenstate which I label as x alpha. It will have some eigenvalues. Those eigenvalues I'm writing as alpha h. Okay. So what is alpha h? H itself is in 2 dimensions, right? H is an element of the, I don't know how should Cartan subalgebra. No, this is not good. This is for the complex numbers. How shall I? I don't know. Okay, let's say Cartan subalgebra. This is a Cartan subalgebra. So, in the SV3 case, this is 2-dimensional, right? So, in principle, I can talk about H1 and H2, right? And for each of them, there will be some number. So, alpha itself is like 2-dimensional, right? Because I have two numbers here. In a more abstractly, what is this object doing? This object is basically, alpha is a map from the Cartan algebra to real numbers, let's say. I mean, some numbers. I mean, at the moment, I don't know whether it's real or complex, but some numbers. We'll see that they're all real. Actually, not only real, they'll be kind of integers somehow, if you choose the basis H1 and H2. But okay, some numbers, which as we'll see later on, that actually it will be real. Okay, so it's a map from a vector space to numbers. And it's a linear map, that's very crucial. It's not just an arbitrary map, it's a linear map. Why is it linear? Because suppose I look at, I have this, I mean, it's a linearity of this. So in other words, if I have an H prime with the X, it will be by definition alpha of H prime X. Now if I take the sum H prime plus H and take the commutator, so if I now take the, say, AH plus BH prime, these are A and B are numbers, X alpha, then that's going to be A H X alpha plus B, this is not good. So if I take AH plus BH prime, X alpha commutator, then this commutator, you just open it up. So you'll get here A, H, X alpha plus B, H prime, X alpha, which will be, well, A alpha, H plus B alpha, H prime, the whole thing multiplying X alpha, right? So, on the other hand, directly from the way we are writing this thing, this object would have been alpha of AH plus BH prime X alpha, correct? So what we are seeing, I mean, this is for any H, right? Any H. So in particular for this is also some H, some H double prime, call it H double prime. Then this would be alpha of H double prime. by this definition in general. So what we are saying is that alpha of this combination is actually just a sum of these two, this object. This is exactly the definition of linear map. Okay? It's a linear map. So this alpha is a linear map from a vector space, C. C is the Karta algebra. In this particular case, we are focusing on that. But now imagine that suppose somebody tells you, I have a vector space, some k-dimensional vector space, right? And I'm considering the space of all linear functions. Now, by function means that it maps any element of this vector space to a number, a real number. Let's say in this case, a real number or complex, doesn't matter. You decide. I mean, okay, whatever. So it's a map so this is a linear map from a vector space to numbers. The space of all such maps is called the dual vector space. Okay, it's a name. So the space of all these maps, the space of all the linear maps from some vector space, let's say from some vector space to real numbers or complex numbers. V is a vector space. This space of all linear maps is, first of all, the statement is that this itself, this space itself is a vector space. I don't know if you have done that. Probably you have studied this in the undergraduate, the linear algebra. No? You might have, or maybe not all of you have seen it. So, and usually I don't know what is the standard notation. And this vector space is called the dual vector space. Dual vector space, 2V. I don't know, maybe it's denoted by V, I don't know, V tilde, I'm not sure. You can choose some convention. I don't know how it is generally in the textbooks they write. But okay, there's some vector space V dual. And very importantly, the dimension of this space is exactly the same as the dimension of that. Okay? If this is, say, k-dimensional, then this is also k-dimensional.
Like the inner product, for example. Exactly, precisely. That's exactly what it is. Yeah. So, because I mean, when you're saying that I mean, some particular map takes the vectors to a real number, that's like you can think of it as the inner product. So, the inner product between V dual and V. That's idea. I mean, okay, you can of course directly prove this, the fact that it's a vector space, because if I give you two such linear maps, the sum of the two linear maps is again a linear map, right? Or multiply a number to the linear map, again it's a linear map, right? So this clearly is a vector space. And then you can easily show that it's the same dimension because you can just choose a basis, okay? Choose a basis which has exactly k elements. Okay? I mean, the way to do that, suppose this is k dimensional, so I can choose a basis, let's call it E1, E2, up to Ek. This is the basis for V, okay. Then I can choose, I can define my linear function. I have to consider after all the linear maps, right? So in particular, let me consider a linear map, let's call it Fi, which has a property that Fi acting on Ej is delta Ij. Okay. So I'm giving you k functions. This I here labels a function, Fi. So I have F1, F2, F3, etc. So F1, for example, gives you non-zero value only for E1, okay, and 0 everywhere else. This is a linear map for each I. And then any F acting on E, any F, I can write it as Fi times some numbers xi, some Dovara. You can see that, because any F by definition, okay, give me, so you have chosen some F. Well, I will ask you, how does the F act on each of these bases, right? So let's say F acting on Ei, Ej, is some number xj, is going to be some number xj, okay? Then I can define this F as that, right? So you see that I can, x are just numbers, and these are k functions, right? And I can expand. I can write any function, linear function map as a linear map as a linear combination of this k linear maps. Right? So dimensionality is exactly the same. It's called dual vector space. So from this point, from this general discussion, then we understand that these alphas are in the dual vector space to the Cartan. Cartan subalgebra is a vector space, right? So here we are not so much worried about the algebra aspect. Here we're just talking about the vector space, linear maps from the vector space to numbers. Okay. So alpha is in the dual vector space. So since in SU3 the Cartan subalgebra is two-dimensional, alpha will also be two-dimensional. Alpha is in the dual vector space, so it will be also two-dimensional. Okay, so that is one thing. Okay, now let's just explicitly compute these commutators to see what we get. So the first statement we want to check is that EK-L, where K is not equal to L. If I just take one of these guys, off diagonal, one of the off diagonal guys, then these are eigenstates of the H1 and H2. Okay, that's what we want to check. So let's look at. I think one thing one can check is in general. First of all, let me just. If I just look at this commutator, I think we did that yesterday, right? What was that? So this is the same as Eij EKL minus EKL Eij. And if you now look at this matrix multiplication, a row here will multiply a column there, right? But here what this is saying that the only non-zero element is the ith row and jth column, right? Ith row and jth column. So the only time you will get something non-zero is when you take the ith row here and multiply this out with some column here. Okay, but when will it get it? I mean, only the jth column. So I'm looking at the ith row. Okay, and here we have all the row, and it's only the jth element. Sorry, jth element is 1, and everything else is 0. Right? That's what it is saying in the ith row. There we have in the now I'm multiplying to a given row. The only time, so here you see only the kth row can be non-zero, right? So this will be only the kth row, and of course the lth. Guys, this will be non-zero. Everything else is 0. But for this row to hit that thing, j must be equal to k, right? So therefore, this guy is in fact delta proportional to delta jk, and then what we will get EIL, because only time this will be non-zero is when it's the ith row and here is the lth column, right? So that is exactly going to be the EIL. If you do it other way, you will get minus delta Li and EKJ. So this is the computational relation of these objects. Okay, so now let's see, we want to check if this is true. So let me take just since H's are really diagonal guys, so let me just, and they can be written as, for example, H1 is E11 minus E22. I don't know whether I wrote somewhere. H2 is E22 minus E33. So let us just look at one of them. Take any one of them, say EII. No summation here. So to pick for each I, I just look at that particular element. Okay. And I look at the commutator of this with EKL. Okay. So this is same I. No sum over I. Well, this is the same as, now we said, so this is going to be delta IK EIL, and then minus delta Li EKI. Now, since this is non-zero only when k is equal to I, I can as well substitute this I by k, right? So this is the same as delta ik, EKL. And similarly here, this I, the only time it will be non-zero is when I is equal to L. So I can as well substitute here L. This was I to begin with, but L. So, both are EKL. And so you see that this is an eigenstate of this guy. So I'm saying that this is the same as delta ik minus delta Li. Okay. The eigenvalue is this. In particular, suppose k was equal to L. So then of course it should vanish, right? Because the two diagonal matrices must commute. Just let's check it if it is correct, whether we have made some mistake in between. Well, if k is equal to L, this vanishes. For any I, no summation over I. For any I, this vanishes as expected. Two diagonal matrices must commute. But when it is not equal, when the k and L are not equal, which means all the off diagonal guys, then using this formula we know the eigenvalue with respect to EII. But actually our case is actually this, because of tracelessness condition, it is these differences which are the basis. So but we can calculate it, of course. So this, by applying this formula here, we see that H1 with EKL gives me, so H1 is E11 minus E22. So you see you get here delta K1 minus delta L1 minus delta K2 plus delta K2 plus delta L2. I'm just substituting, for this guy I substitute I equal to 1, and for this guy I substitute I equal to 2, and take care of the minus sign. Okay, so we got that. Similarly for H2 with EKL is, now this is 2, and 3. So you'll get here delta K2 minus delta L2 minus delta K3 plus delta L3. Any questions? Yes. Okay, so our notation was, we called X alpha 1 as, in fact already you can see from here, so okay, X alpha 1 in our notation was E12 I think, X alpha 2 was, I don't know which one. Okay, let me just use the same notation. X alpha 2 was E23, and X alpha 3 was E13, right? These are all upper triangular. And then the transposes of them were the lower triangular. So X minus alpha 1, this is just a notation. I mean, it's a convenient notation as we will see. This is E21. The transpose of that is simply this. X minus alpha 2 is E32, and X minus alpha 3 is equal to E31. Now notice that if I exchange L and K, that's what is happening, right? When I do the take that from going to the pluses to minus, X alpha 1 to X minus alpha 1, I'm exchanging these two indices, right? So if I exchange K and L, what has happened? You pick up a minus sign because this is antisymmetric in K and L, right? So you pick up a minus sign. That means this guy will have exactly, what if suppose this has some eigenvalue, then this will have exactly the negative of that. Okay, that's the reason why it's called, we have put the minus here. It's just like in SU2 case, you had what we call sigma plus and sigma minus, right? Sigma plus, the eigenvalue for sigma plus was plus 1. Sigma minus was minus 1 or plus 2 depending on normalization, plus 2 and minus 2 depending on normalization. But the crucial thing is that these two have opposite signs. for the eigenvalues. And the same thing with these two and these two. That's the reason for this, putting a minus sign there. Okay. At any rate, let's just compute these values. So for example, so let's look at the E12. So E12, H1 with E12 is, what is it, 1, 2. I have substitute 1, 2. So this vanishes. Huh? No, so K is equal to 1 and L is equal to 2. So this is 1, okay, this is 0, that is 0, right? K equal to 1, L equal to 2, and that is 1. So 1 plus 1, 2, right? So you get here 2 E12. And H2 with E12 with the same guy will be, now we have E12 with H2. So K is 1, so this vanishes, L is 2, so this is there. K is 1 and L is 2, this vanishes, so you get here minus 1. Right? So you get here minus E12. Okay. Now let's do also for all the other three. So we have H1 with let's say E23 gives you, now you put K equal to 2, L equal to 3, K equal to 2, this not there, that is there, K equal to 2, L equal to, this is not there, so it's minus E23, and H2 with E23 gives you, now we have 2, 2, this doesn't get 3, 3, 3, 2 is 0, this is 0, that is 3, 3, so 2, 2 E23. And finally, we have the last one, which is H1 with E13, H1 with E13, and H2 with E13. So E13, so 1, 3. So there is this here, nothing else, right? So just 1 equal to E13, and H2 with E13. There is nothing here, this plus again, right? So plus E13. I don't know if I have made some mistake, I mean, silly mistakes. Yeah, I think it's correct. Huh? Okay, so this is the, and now I don't have to calculate for these guys, because these guys I know it will be just exactly the opposite signs for these three objects. But these are generally, I mean, one usually calls them, these are called positive, these alphas are positive roots, and here these are negative roots. Okay, this is terminology which will become more clear later. And this is a statement that we find that for every positive root there exists a negative root. This is rather interesting, right? That for every positive, I mean some set of eigenvalue, there is also exists another set with exactly the negatives of them. No? So the two eigenvalues come in pair. They always come in pairs. Now I could draw a picture here. Let me just try to draw a picture here. I will. This picture is just a kind of suggestive picture. So I will draw the roots here. So let's say I draw the eigenvalues with respect to the H1 here, and eigenvalue with respect to H2 there. Okay. So let's look at the E12. So E12 has 2 units of this one and minus 1 unit of this one. So it is somewhere here, right? This is 2 and minus 1. So this is 2. So this is 1, 2, etc. And here is minus 1, 0, 1, etc. No? So I'm just plotting this, the eigenvalues. Since there are 2 values, I have to plot it in 2 dimensions. This axis refers to the H1 eigenvalue. This axis refers to H2 eigenvalue. So this guy, so this corresponds. So this is what we call alpha 1. Okay? Because this is what we were denoting X alpha 1. That's that. Then this one is minus 1 here. So with H1 it's minus 1, so it comes here, and 2 units here. So this is alpha 2. Picture is not very good, but okay. And so alpha 2. This is alpha 1. Okay, that is alpha 1. And alpha 3 is, alpha 3 will be plus 1 plus 1. So it's somewhere here. And there are negatives of them. Those are these three roots, right? But the negatives of them, and since eigenvalue is exactly the opposite, it will be just extended to the negative direction. Okay. So this will be minus alpha 2, this will be minus alpha 1, and this will be minus alpha 3. Now this picture looks a bit not so nice, right? Not so nice. But nevertheless, the reason why it's not so nice is because the things that we have chosen here, H1 and H2, they are not orthogonal in the sense of, you remember when we talked about the trace, taking the trace, product of the traces. If you look at the trace of, in the Gell-Mann matrices, we had lambda 3 and lambda 8. This was 0. In fact, in Gell-Mann matrices, you have lambda I, lambda j was proportional to delta ij with a factor of 2. But important thing is proportional to delta ij. Whereas these guys are not satisfying that. The trace of H1 with H1 is 2. Trace of H2 with H2 is also 2. But trace of H1 with H2 is not equal to 0. It's, what is it? Is minus 1, right? Is minus 1. Because H1 was 1, minus 1, 0, H1. H2 is 0, 1, minus 1. So when I take the product, I will get a minus 1 here and take the trace. So they are not in some sense orthogonal. Although I have not defined to you what is a metric, this will be a subject of one of the, probably next week I will talk about it. But for the moment, just assume, just accept that this defines a metric on the space, on the vector, on the Cartan, or actually full Lie algebra, but in particular Cartan space. Okay. If so, the reason why we are finding such a distorted diagram, it's basically like a hexagon, right? Except the lengths are not all the same, and the angle is not 60 degrees. But that's happening because we have chosen not an orthonormal basis here. For example, let's plot it with respect to this Gell-Mann matrices. Gell-Mann matrices satisfy that, right? And remember, what was Gell-Mann matrix? Let me just draw that picture just to show it to you. I think that picture is better to draw. So basically remember what it was. H1 was lambda 1. So lambda 3 was H1. But lambda H2 was square root of, what was it, square root of 3 lambda 8 minus lambda 1, right? Divided by 2 or something like that. I think if you look at the lambda 8 had a 1 over root 3.
Minus
so that root 3 is to get
minus lambda 3.
That 3. Minus lambda 3, correct. So this was the thing. So in other words, therefore, I can invert it. So lambda 3 is H1, right? And then I can take it on the other side. So we have lambda 8 is 2H2 plus H1 divided by root 3, right? Okay. So now I can just, since I know the eigenvalues with respect to H2 and H1, I know the eigenvalues with respect to lambda 8. So H1 is the same, but this tells me that lambda 8, H1 is the same as lambda 3, so I don't have to work there. Lambda 8 with the E12 is, what is that? So 2 times H2 plus H1, which is 0. You see, 2 times this plus 1 times that. Minus 2 plus 2 is 0, right? So this is 0 actually. Similarly, if you look at now from here, I look at lambda 8 with E23. Well, that gives me here 2 times 2, 4, minus 1, 3, divided by root 3 is square root of 3, right? So you get here square root of 3, E23. And from here, lambda 8 with the E13 gives me 2 minus 1, which is 1. So it is 1 over root 3. So these are the eigenvalues, right? Lambda 1s are already, lambda 3s are already there. So now let's plot. Now let us plot. Now, and the plot will be very, very beautiful plot. So now I plot, again now the eigenvalues of lambda 3, which is the same as h1. And here the eigenvalue I'm plotting is lambda 8. Not h2, but lambda 8. So first let's look at the first guy, E12, alpha 1. This one is 0. So it is purely in the x-axis, I mean the horizontal axis. And the value is 2. So you get here 2. So this is 1, this is 2. Okay, so this is alpha 1. Okay, in this basis. What about alpha 2? Alpha 2, you see minus 1 here. The h1 eigenvalue is minus 1. But lambda 8 eigenvalue is root 3. Okay, so you find here minus 1, it comes back here, and the square root of 3. But that, you see, if you look at the length square of this vector, so this is 1, minus 1, so this length is 1, so use the right angle, I mean the Pythagoras theorem, right? 1 plus square root of, this is square root of 3, so square root of 3 square is 3, 3 plus 1 is 4, and take the square root, so its length is also 2, exactly like that. Okay. Not only that, you look at this angle, tan of this angle is simply root 3 divided by 1. Okay, so this angle is 60 degrees. Okay, which means this angle is 120 degrees. That's alpha 2. Now let's look at alpha 3. Alpha 3, we have plus 1, no sorry, alpha 3 is, yeah, plus 1 and 1 over root 3. Is that correct? Yeah. So plus 1 here, so plus 1, and is it 1 over root 3 or root 3? 2 plus, root 3, sorry, this is root 3, correct?
Minus.
No, 2.
Should be minus.
This is 2, 2 minus 1 is 1 over root 3, right?
2 plus 1.
I'm confused. Is that correct? Is it 1 over root 3 or? Root 3. How do you see that? And I'm missing. So this.
2 plus 1. 3.
Plus 1. Correct. I was looking at minus. Thanks. So this is root 3. Good. Okay. So now we have 1 and root 3. It's here. Picture is not very good. Something like this here. Okay. And again, this is root 3. So this angle is 60 degrees. This angle is 60. This angle is 120. And the lengths are the same. Okay. And then, of course, the negatives of them. The x minus alphas have negative roots, negative values. So there is this here, this here, this here. And you have a perfect hexagon. This is a perfect hexagon. So maybe let's draw this picture here completely. So okay, good. Now, okay, so this is done, and I just keep the picture here because from this picture we can learn a lot. Just for the moment, I just leave that here. Any questions at this point? I mean, it doesn't matter. One could have also worked with this. It's not a problem. Huh? Except that it looks a bit confused, this picture. Right? Yeah.
Our aim was to solve an eigenvalue problem for the B bracket of H over some other matrix.
Yeah.
And we said that if you choose those special matrices, upper triangular ones, strictly upper triangular ones, we would find all the solutions. It was like a guesswork, and it's worked.
Yeah.
Do we know that those are all possible eigen values?
Because there are 6 dimensions. I mean, the total dimension is 8. Cartan algebra is 2. So remove the 2, while remaining guys are 6 dimensional. right? And when we have found the 6 eigenstates,
Then we have done.
then we are done. It's just because, I mean, all the off-diagonal matrices I can expand in this basis, right? EKL when K is not equal to L. And each of these EKLs are actually eigenstates. So that's exhausting.
If you would have chosen another Cartan subalgebra,
Of course, then it will be different. Yeah.
but in the end, are we doing the same thing if we choose another
Sure,
subalgebra?
and you'll again end up with the same picture. Yeah. This is easier.
But more complicated calculations.
It will require more because now that means already the Cartan itself is not diagonal. So then calculation will become much more complicated. For example, you could have chosen sigma 1. Sigma 1 from the first SU2 and perhaps something else from the somewhere else which commutes with it. Yeah, you could do that. Yeah, for example, you could choose sigma 1 and lambda 8. That would be perfectly okay. Right? But then the calculation is more complicated.
What we draw here are eigenvalues or eigenvectors?
Well, I mean, this alpha is the eigenvalue, but alpha itself is two-dimensional. That's why this is a plot of alphas. So x alpha 1 has this eigenvalues. I mean, but there are two eigenvalues. That's why I'm plotting it.
Eigenvalue vector.
Eigenvalue vector, yeah. Although, there is, when they say root vector does not mean this. Root vector is the x alpha. So there is a root here. This is a root. When people usually use the word root vector, by root vector they mean this eigenvector x alpha 1, for example. This is this spans a one-dimensional space, right? In the full algebra. So this is what's called root vector. But yeah, I mean, so for this one just uses the word root. But it's understood that root has the same dimensionality as the dimension of the Cartan's algebra. Okay, now let us, so what have we done so far here? So we have taken all these off-diagonal guys, and they are eigenstates of this. So we know the commutation relations of, first of all, Cartan commutes with Cartan, and then we also know the Cartan with everything else, right? But we don't know, we still have to work out the commutation relations between these guys. That we haven't worked out yet, right? Okay, so let's try to do that. Again, we had this formula which I erased it again. I should write it down somewhere. Eij EKL commuted was delta JK EIL minus delta LI EKJ, right? So this is so we can use that formula to just get all the computation relation between these different x alphas. No? So let's see. So where is it? What happened? Here. Sorry. So let's look at x alpha 1 with x alpha 2. X alpha 1 with x alpha 2. So this is we said this is the same as E12, E23. This commutator, if I use that formula, so you have a delta, Kronecker delta of this is not 0, right? But the Kronecker delta of that is 0. So the second term is absent, but the first term just gives me E13, which is the x alpha 3. Okay. And then we can, similarly you can show x minus alpha 1 with x minus alpha 2. So this is the same as E21, E32. And this time you will just get minus E31, again using that formula, which is the same as minus x minus alpha 3. What about, let's look at this. What about x alpha 1 with x alpha 3? This gives you, well, this is the same as E12 and E32. E12 and x alpha 3 was E13, sorry, E13. This time it is 0, right? Because neither these two indices are equal, nor those two indices are equal. So both the Kronecker deltas are 0, right? So that's 0. Similarly, x alpha 2 with x alpha 3. This is E23 and E23 and E13, right? Again, this is 0. Okay, so let's see, let's look at this picture here. So we said this is alpha 1, this is alpha 2, this is alpha 3, and then here is minus alpha 1, minus alpha 2, minus alpha 2. Okay, first thing we notice, okay, so let's see, x alpha 1, x alpha 2 commutator gives you x alpha 3, right? That's not so. So, but that, I mean, if you just look at this this alpha 1 and alpha 2 and add that up vectorially, you know, I mean, in 2 dimension, you exactly get that. Okay. On the other hand, if you look at these things which are 0, x alpha 1 and x alpha 3 is 0, well, alpha 1 is here, alpha 3 is here. When you add these two vectors, you get somewhere there, but that didn't exist. I mean, there was no such state with that eigenvalue. That's the reason why these things vanish. Both this and this. Because alpha 2 and alpha 3 will give you something vector out there which doesn't exist. Okay? Because we have a list of all the eigenstates. That's it, all the eigenvalues. Nothing more. Okay? So that is what's happening. And it's not hard to understand why this is the case. Why when you take the commutator, you get something where these are additive. These, why are they? That is for the simple reason, now I can erase something here. Let's see, what can I erase here? Yeah, maybe here I can erase this. I mean, if I take a commutator of H, so suppose I look at this commutator x alpha, some alpha and x beta. Alpha and beta could be any one of these six guys. Huh? X alpha, x beta. Then, I want to ask, what is this object? What is its, what will be its eigenvalue with respect to the Cartan generators, right? So suppose I ask that. So I look at this, to answer that, I want to ask this question. Is equal to some number times x alpha, x beta, right? So if it is an eigenstate, then it should satisfy that, right? There will be some number depending on h, so some, I don't know, some function, let's call it gamma h, right? Like that. So let's see, is it true? Well, we can just use the, use the Jacobi identity. We know Jacobi identity is satisfied. So Jacobi identity says that this is the same as h x alpha x beta minus, plus, we can check that, we'll just check it. X alpha h x beta. Okay, let's check that. So what is it? So I can bring it on the other side, right? We are saying that this is equal to that by Jacobi identities. Huh? So is that true? Are you convinced by that?
Minus.
Is there a minus sign? Well, this is the same. I can put it in this. I can put this in the same order, right?
Yeah.
So this will be minus x beta h. So this is the same as minus x beta h x alpha, right? And so let's see. So what I've done here. So if I take it on the other side, it will be plus. That's exactly cyclically moving, right? X beta goes there, h comes here, x alpha comes there. That's one. And here, alpha has gone there, x beta has gone there, and h has come there. But because when I take it on the other side, I have a minus sign, right? So this exactly, Jacobi identity tells you that this is equal to that. Okay? Actually, the best way to remember, instead of doing all the cyclic, etc., is this Jacobi identity it's like a derivative. It acts as a derivative. Imagine that this was a differential operator, okay, acting on this thing. Well, use the Leibniz rule, right? So Leibniz rule says it will be the same as first taking the derivative here, which is like, I'm thinking of h as a derivative operator. So this is like taking derivative of that, Huh? And then another time, next when it takes a derivative here, which is that. So it's really, this is like a derivative. Actually, this analogy goes quite far. I mean, it's not just, it really, you can think of it as a derivative. This commutation relation is like a derivatives, in some sense. But this is the easiest way to remember. Instead of, trying to do cyclic, you can always make mistakes in the cyclic thing, So, but this here is just like this rule. Okay, if you agree with that, then you see, this is already an eigenstate. So this is simply alpha h times x alpha. Alpha h is a number, so I can take it out. Okay. So the first term is alpha h times the commutator x alpha x beta. And the second term, this is again alpha beta. Beta of h times x beta, right? This is again an eigenstate, so it's a number which we according to our notation, it will be simply beta of h, right? So again, so that will be plus beta of h times the same guy. So you see, gamma of h is the same as this plus that, right? So therefore, we conclude that this guy is alpha of h plus beta of h. Okay. So two things we learn. We learn that if this is an eigenstate and that's an eigenstate, the commutator is again also an eigenstate. And secondly, we also know the eigenvalue. Eigenvalue is simply the sum of the eigenvalues of this and that. This is the alpha n. Okay. This is the reason why the commutator is, this happens. This is not a miracle. I mean, you should have expected it, right? That when you look at the commutator, the result will have the eigenvalue, sum of these two eigenvalues, alpha 3. Right? And in those cases where the sum doesn't exist, then the commutator must be 0. Because we have exhausted all our possible eigenstates. No?
Which commutator must be high?
This one, for example, this guy, look at this one. This commutator is at 0, right? This was alpha 1 with alpha 3. Alpha 1 is here, alpha 3 is here.
Also, we did the previous calculation, like not specifying alpha and beta, and said that commutator of x alpha and x beta is always an eigenvalue of this H operation.
Yeah.
So, and it works additive on alpha.
That's
vectors.
right.
So either they belong to the alpha space.
Yeah.
So we find the next result,
Right.
or it
still
must belong to that space.
Yeah, it must be 0. Of course, this is equality, right? But it could be that this itself is 0. In fact, if this is not in the list of the eigenvalues that you have already constructed, then this tells you this must be exact, this will be 0. Because if you would have found this, right? Because we were looking at all the off-diagonal guys. So everything outside the Cartan we have looked at, and those are the only eigenvalues we have found, right?
Is 0 vector also an eigenvalue of H commutation operation?
I mean, if it is 0, H with 0 is 0, right?
Yes. Can we define like can we name it as an eigenvector?
No, I mean, there's no meaning because I mean, 0 is just nothing. I mean, trivial element. Yeah, this is a trivial element. 0 is. Yeah. This is like, I mean, the discussion about the highest weight and so on when we were doing SU2. Now, at some point, it annihilates. So
because there is no more eigenvalues.
No more eigenvalues in that representation. Yeah. And then you can work out everything. So I mean, actually, this is telling you directly that so whenever you take the commutators of this off-diagonal guys, the result will give you the something which you can obtain from this addition of these roots. So, for example, if I take this guy with that, so this is x minus alpha 1, that is alpha 3, you are going to get this. And indeed, you can check, you can work it out, and you can show that by just using that formula, you can show that that will give you x alpha 2, and so on. Okay. Now, what happens to this? I mean, there's one more possibility here, which we have not looked at. What happens to this if I take the commutator of x alpha 1 with x minus alpha 1? Okay. Now, adding these two eigenvalues gives you 0. What does it mean, 0 eigenvalue? It means it must be a Cartan element, right? The Cartan space, since they are commuting, they are 0 eigenstates, right? Okay? They commute with the Cartan. Cartan is a commuting algebra. So H1 will commute with all the Cartan generators, H2 will commute with all the Cartan generators, right? So when you see the eigenvalue equal to 0, that is telling you that that is in a Cartan subspace. Okay? So let's just check that. So if I compute this again, let's now use the x alpha 1 with x minus alpha 1. So let's see, I can erase this part here. So if I take x alpha 1 with x minus alpha 1, well, that's the same as x alpha 1 is E12 with E21. And what am I going to get? So there will be the first term gives you a Kronecker delta of that, and you get E11. Okay. And the second term there is a Kronecker of these two indices, which is again delta 11. And then the minus sign here and E22, which is the same as H1. Similarly, if you take x alpha 2 with x minus alpha 2, so this is x alpha 2 is E23 and this is E32. So this gives me E22 minus E33. So again, diagonal. You see, these are all diagonal matrices or Cartan generators. Of course, traceless, because they have to be traceless. And finally, x alpha 3 with x minus alpha 3, which is E13, E31, and that is E11, yeah, minus E32. Okay, so these are all combinations. So for example, the E22 minus E33 was exactly H2, right? And this one is H1 plus H2. So it gives you back the Cartan generators. Okay, so now let's again look back at this picture, and you see. So let's focus on this guy. Let's focus on this guy. We have x alpha 1, x minus alpha 1, and H1 together forms an SU2 subalgebra. Because the x alpha 1, x minus alpha 1 gives you H1, and H1 with x alpha 1 gives you back x alpha 1, and H1 with x minus alpha 1 gives you again back x minus alpha 1, because these are eigenstates. Okay, so this forms an SU2 subalgebra of the yeah. I mean, this was just the matrices in the where we had the third was 0, third row and third column was 0. You had, and here we just put sigma matrices. No, those were the alpha 1, x alpha 1, x minus alpha 1, and H1. So it's not surprising this is an SU2 subalgebra. Okay, so this is fine. So that's an SU2 subalgebra. But now let us see how. So I have these three generators: x alpha 1, x minus alpha 1, and H1. H1 here you can think of it as like there are two guys, right? Because Cartan subalgebra has 0 weight, 0 eigenvalue. So here as if two guys are sitting here, H1 and H2. But if I look at these three generators, then SU2. Now you can ask the question: what happens to the remaining guys? They must be coming in some representation of this SU2, right? I mean, and we know all the representations of SU2. Meaning that when I look at the commutations of x alpha 1 with these remaining guys, right, that should give me some representation of SU2. Okay. This one is the adjoint representation. These three, x alpha 1, x minus alpha 1, H1, that under commutation relation just gives you a joint representation, right, of the SU2. But now if you look at this guy, for example, let's say, and I apply x alpha 1. Apply meaning take the commutator. We are adjoint representation. When you apply, it means taking the commutator. Now x alpha 1 with x alpha 2, x alpha 1 with x alpha 2 gave you x alpha 3. And x alpha 1 with x alpha 3 is 0. So this is the highest weight state. with respect to this SU2, right? And in fact, this representation is a doublet, spin half representation of this SU2, right? Because, I mean, you can also check if I apply, so think of this as a raising operator. X alpha 1 is a raising operator. J plus, I think we were calling J plus, right? I'm not sure. J minus. So this is a raising, that is a Cartan. I mean, this guy is a Cartan, H1 is a Cartan. And now I apply J plus on this, I go there. When I apply J plus there, it is 0, right? Similarly, if I apply J minus here, I come here. J minus is simply take the commutator of X minus alpha 1 with X alpha 3, you will find you will get X alpha 2. But now I apply further J minus, there's no way. If I look at adding these two guys, I would end up something here, but that doesn't exist. So J minus, which means X, what am I saying? No, not here, sorry. X minus as well. J plus I call X alpha 1, and X minus alpha 1 I'm calling as J minus. Because I'm focusing on this SU2. Okay? So this J minus acting on that gives you 0. Okay? So this is the lowest weight state of that representation, and that's the highest weight state of the representation, and they're just exchanged by the action of this SU2. Moved around by this SU2. So this is a doublet representation of this SU2. Right? Spin half. And the same thing happens here. You see, this SU2 will just move you between this and this. This will be the highest weight, that will be the lowest weight. Okay. Yeah.
The upper and below ones are separately satisfying spin 1/2 representation.
Yeah, for this SU2.
For this SU2, but are they satisfied at the same time or separately? You mean we had a unique high state? In this case, do we have also a unique high state, or the right ones both are the high states?
Both are high states. Each of them gives you one spin half representation. So there are two. I mean, you can have a number of. So the full thing is, of course, reducible representation of SU2. The full A-dimensional SU3 is A-dimensional, right? Adjoint representation. That A-dimensional space splits into the adjoint of SU2, the three of these guys, and two doublets, and one singlet. Because if you add 3 plus 2 plus 2, it's still 7. So we are missing one. And that is this combination. I mean, a particular combination of H1 and H2, or actually H2, yeah, H1 and H2 should commute. That lambda 3 combination. See, lambda 3 combination will commute with X alpha 1 and X alpha 2. Both X alpha 1 and X minus alpha, plus or minus alpha 1. This is easy, lambda 3. That's easy to see because lambda 3 in this block, I mean here, see the SU2, this SU2 that we are talking about is here, right? Everything else is 0. But lambda 3 is lambda 8, sorry, lambda 8. What did I say? Lambda 8, I'm sorry. Lambda 8. Lambda 8 is 1, 1, and minus 2, right? So this is identity matrix here. So that's going to commute with this SU2. So the singlet is lambda 8.
What kind of linear combination gives lambda 8 with X alphas?
Yeah, lambda 8, I think I erased it.
2x?
Lambda 8, I don't know, I just wrote it down before, I just erased it.
Root of 3, 2h1.
Yeah, square root of 3, h1 plus h2, right?
2h1.
Was it 2h1?
Yeah, 2h1.
Okay, 2h1.
So this is also an element of Cartan's algebra.
Yeah.
So we cannot show it on this plot.
Yeah, that's what I said. I mean, you should think of this as like there are two objects sitting
So
there.
the single state is that.
Yeah. The 0. If you look at this is a plot of eigenvalues, no? So eigenvalues of this guy is 0 because it commutes, right? With the Cartan. Cartan is a abelian, so it's all there. So you should think of this like here there are two. It's a two-dimensional vector space sitting here. Here, these are all one-dimensional vector space.
6 are outside, 2 are inside.
2 are inside, yeah.
That's 8.
Yeah. And the way it splits under this SU2, under the SU2 of this guy, so the SU2 we are looking at is X alpha 1 x minus alpha 1, and h1. Right? We saw from this algebra that they formed an SU2 subalgebra. Right? So we're looking at that. And now we are splitting the 8-dimensional representation in terms of that. Right? And you see what is happening. So there is an adjoint here, because this is of course part of the 8. Right? Then there is a doublet here. So we have x alpha 2 and x alpha 3. They form a doublet, with this being the highest weight, that being the lowest weight. And similarly, I'll have x minus alpha 3, minus alpha 2, x minus alpha 3. Again forms a doublet, with this being a highest weight. Okay. And then finally we have lambda 8, which commutes with the entire, all this SU2 throughout. Of course it commutes with that is obvious, because it's katna, but also it commutes with this. Okay. So that's a singlet. So 8-dimensional has been split into triplet, 2 doublets, and 1 singlet. Okay, but this is this SU2, but there are several SU2s floating around here. You see, you could have taken this SU2, treat this as a raising operator, that is a lowering operator, and then there will be some combination of H1 and H2, which will enter. We can check x alpha 3 with x minus alpha 3 is H1 plus H2. So call this H1 plus H2 as the J3 component of that, of this SU2. Then with respect to that, with respect to this SU2, again we have an adjoint representation, one doublet here, one doublet there, okay, and then there is a one singlet. And finally this SU2, same thing, this SU2, we have an adjoint here, one doublet here, one doublet there, and a singlet. So you see, this picture is, really beautiful picture, you know.
Did we take, there were 2 elements we can choose from the center. One belongs to the triplet state, one belongs to the singlet state.
Yeah, so depending on which SU2 you're talking about, one of them will be part of the triplet, one combination will be part of the triplet, another combination will be singlet. But this will change as you change the SU2s.
So what are the triplet states in terms of alphas? What are elements of?
Yeah, so it will be just these guys, whatever appears here. So for example, for this SU2 subalgebra, what appears to the right hand side, that will form the J3 component. Here it will be, for this SU2 subalgebra, it will be H2. And then for this SU2, this will be this combination, H1 plus H2 combination. Which is not surprising again, because what was alpha 2? Alpha 2 was, alpha 2 had this block structure. X alpha 2 and x minus alpha 2 had this block structure. You had one, here you had, in this block you had a sigma 1, sigma 2, sigma 1 and sigma 2. Yeah. In this. And the combination, one combination was x alpha 2, other combination was x minus alpha 2. And H2 is exactly the guy which is sigma 3 here. Right? H2 was that, we defined H2 like that, 1 minus 1. Okay? So these three form an SU2 subalgebra. Okay? And now look at this guy, alpha 3 minus alpha 3. What is the structure here? Alpha 3 minus alpha 3 was this one. This was one of them. Alpha 3 was that, and minus alpha 3 was 1, 0 here. Okay. Then it's clear which will be the J3 component. It will be 1, 0, minus 1. Right? Because you see, we are removing this guy and looking at this part, which is, so this was the sigma 1 and sigma 2. After removing that, so similarly you remove this will be sigma 3. And H1 plus H2 is exactly that. Okay. So this is completely fixed. Yeah? And now to find the other combination, which is singlet combination, you need to find out the other guy which commutes with this, right? Because you want a singlet, so it should completely commute with all the SU2 generators, right? So that is why in this particular case it was lambda 8. Now here, what will it be? Here,
minus 2, 1, 1.
Yeah, so in this case it should be, what will it be? So yeah, it will be something like minus 2, 1, 1, minus 1. No, it should be 1, 1, minus 2, right? That combination for this case, right? So okay, find the combination of H1 and H2, which gives you that. That will be the singlet. Okay. Whereas here it would be 1, 1, minus 2, right? So once again, find the combination, which will give you that. So, okay. So it's a very beautiful structure in this. I mean, and this persists in all the Lie algebras. I mean, simple Lie algebras. This will persist, and this is what allows us to really systematically study these Lie algebras. Okay. Yeah. So yeah, this are the. Is there anything else I wanted to say here before? Since the pictures are all here, so. Okay. Yeah. You have any questions? Any questions, comments?
Why all the operations are acting on other elements other than finding a vector space? I mean, for example, is it when we take the commutation with X alpha, is it like taking a combination with ladder up operator, creation operator, sigma plus?
Well, I mean, so what are we at the moment we're looking at adjoint representation. In adjoint representation, this acts on the Lie algebra itself, right? So the vector space is the Lie algebra itself. So Lie algebra is mapped to the Lie algebra. So that's what we're doing. So so that's why we are using the word it's acting on. So X alpha is acting on.
When we take commutation with X alpha, it is like taking commutation with sigma plus, which means the adjoint representation of SU2 in the order.
Yeah, I mean for this part, if I just focus on these three guys, this and that will do. But I have also not just that, I have other guys, no? Other commutation relation, X alpha 1 with X alpha 2.
It is, but if I take the computation of X alpha with alpha 2 element,
X alpha
is it like raising it to alpha 2, 3?
Yeah, exactly. Yeah. So I mean, yeah, it's simply the I have this big space, right? I have this 8-dimensional vector space. That is the Lie algebra, right? And the adjoint representation is acting on this guy, no? But now I don't look at the full adjoint representation of SU3, but I just look at a subalgebra, and some particular SU2 subalgebra. And I ask the question, again, I look at how these guys are acting on this full Lie algebra. And we find that it's not reducible under this SU2 subalgebra, which is to be expected. And we can answer more. We can say precisely what, when you reduce, you can decompose into irreducible representations, and we know precisely which ones are appearing, right? 1 triplet, 2 doublets, and 1 singlet. Yeah. So this is, and you see, maybe I can just mention this. Just because the picture is there. You remember that for any SU2 representation, irreducible representation, we had a symmetry, right? For every m quantum number, you had a minus m quantum number also, right? There was a perfect symmetry if you reflect. And this is exactly what's happening here. So if you look at, for example, this SU2, then I know this is going to be a doublet here, this is going to be a doublet here, and okay, this is a triplet and a singlet, right? That means if I draw a line perpendicular to this line, then the whole picture must be mirror symmetric. But this you could have done with any SU2. So if I took this SU2, I have a mirror reflection around this plane being perpendicular to that. Similarly, if I take this SU2, I have this plane which is perpendicular and it's reflection symmetry. Or if you take now third SU2 is what? Third SU2 is this one, let's say, this one. Then I have a plane perpendicular here and it's reflection symmetry. So this is the reason why the patterns are so beautiful, you know? Because there's a huge amount of reflection symmetry. Of course, I mean, this was because I used this basis. I mean, if I had used H1, H2 basis, picture looks ugly, right? But it has this hidden symmetry because after all, it's a matter of changing the basis, no? And you suddenly uncover this beautiful symmetries here. Here, you don't see it because you have chosen a very strange metric, you know? That is why you don't see it here. Yeah.
My question was actually, why are we using always a joint representation? Why don't we try to find another representation?
Oh, we'll study
like
also others, but a joint representation is what captures the Lie algebra itself, you see. So we want to understand the Lie algebra structure itself first.
For example, using that, we could reduce it into 4 parts using this additional property of alpha vectors. Are we using it to see how many components of less dimensional Lie algebras, a bigger Lie algebra consists of? Are we using to reduce it? Just
No, not really. This is just to understand the structure. Yeah, I mean, in a sense, I mean, if I focus on this SU2, yeah, that's what I'm doing, right? But what this is saying basically, now this is not just SU3, but what this kind of argument, this will be general argument. What we will see that for every non-zero root, I mean, so alphas, no? For every non-zero root, there is an SU2 subalgebra. And then everything else must fall into these representations, right? And this gives you very strong conditions. I mean, it really is so restrictive that there's not much freedom. You know. In fact, that's why people are able to completely classify all possible simple Lie algebras by just using this this restriction that you get. Every non-zero root means there's an SU2 subalgebra corresponding to that. Right? Because for every root there's also a negative root. This is a general feature. And these two combined together with a particular combination of Cartan will always give you one SU2 subalgebra.
And we are always sure that we can use the adjoint action on other elements.
But that is by definition, because the Lie algebra comes with a Lie bracket, right? For all the generators, the Lie bracket is defined already. So,
like you said, the adjoint representation comes for Fourier.
Yeah.
When we have Lie bracket structure, it satisfies the representation concept. This is direct.
This is direct.
Independent of the figure.
that's so tomorrow we'll now go to the fundamental representation itself. And again, fundamental representation is 3 by 3 matrices. That's already.
But the vector space is different, not the same elements. In that case.
Yeah, in that case, it's a 3-dimensional, right? I mean, here the joint representation will be 8 by 8 matrix, no? Because an 8-dimensional. I mean, so now we are thinking of acting on an 8-dimensional space, and it maps to an 8-dimensional space. So I should always be able to write it as an 8 by 8 matrix.
Yes,
right?
but it does not look like a diagonal from plus j to minus j matrix for the j.
No, the Cartan will be diagonal.
Uh-huh.
Cartan will be the diagonal. A joint representation of Cartan, because we already decompose everything else in terms of the eigenstates of that. So Cartan will be diagonal. So if I write Cartan, so for example, H1 will be, I can not erase that part, writing in terms of all the, so for example, if I 8 by 8 matrix, so say this is acting on, let's choose some basis, H1, H2, X alpha 1, X minus alpha 1, X alpha 2, X minus alpha 2, and X alpha 3, X minus alpha 3. Right? So these are 8 vectors. And so I'm going to look at, so this action will be, I should be able to write it as 8 by 8 matrix, the way this commutator acts. No? So if I look at a joint of say H1 itself, let's see what happens. So it's just, so 0 eigenvalue here, 0, I mean, the commutator is 0, right? And X alpha 1 is, I think we wrote it down somewhere, I don't know. Yeah, X alpha 1 is here, so it's a 2. X minus alpha 1 will be minus 2. X alpha 2 is minus 1. Then minus alpha 2 is plus 1. And here it is 1 minus 1, right? This for H1. Similarly for H2, you just look at these eigenvalues. And that will be, so it's diagonal matrix.
Yeah.
But if you now look at the X alpha 1, let's look at the add X alpha 1 itself. How is it going to look like? So it will act on H1 and it will give you X alpha 1, right? So this is going to be, how shall I put it? So it acts on H1 and gives you, so probably it's like 1, 0, 0, right? So, I mean, I have to fill up everything, but I'm just saying, so this, when you multiply, it will give you that. So when it adds on to H1, or it's other way around, it's a question of active or passive, you know. Transformation is active or passive, that's always confusing. Yeah, maybe it's other way, doesn't it? Yeah, something like
Yeah,
that.
it was right. It takes 1 to the.
Yeah, exactly, so it takes you that. H2, instead of H2, let me put here lambda 8, because that's easier. Lambda 8 is singlet of that, no?
Yes, how should I say? We decompose it into 4 parts.
Yeah,
If
yeah,
we
yeah.
choose the right elements there, we would reduce into a
That's
specific 4 of them.
Yeah, yeah.
The matrices are only
Exactly.
interacting.
So it will be exactly, so since alpha 2 and alpha 3 forms a doublet, if I, suppose I just change it, put here alpha 3 and x minus alpha 2. Then this will be a doublet. So here I will find some doublet structure here, everything else 0. Here again, doublet structure here. So here it should be just like a kind of, x alpha 1 will just erase it, right? It will take alpha 2 to alpha 3. So presumably something like that. Okay. And this one will be, I think, minus alpha 3. So something like this, maybe some such thing. It moves there. And here it will be in the, so put lambda 8 here. Lambda 8 will be all 0, 0, 0, 0, everything 0. And these 3 will form the adjoint representation. So there will be some 3 by 3 matrix here and everything else 0. No, that will be the structure. This 3 by 3 matrix will be exactly doing this raising operators. Acting on H, it will give you x alpha 1. Acting on x alpha 1 should be 0. Acting on x minus alpha 1, it gives you H1. So that you can write down the matrix like that. Yeah, so far we are studying adjoint. Tomorrow we'll study the 3-dimensional, which is defining representation, fundamentally. So which is, when you write this 3 by 3 matrix, it is already acting on a 3-column vector, right? But then you can again look at the eigenstates. You can take the 3 eigenstates, no? And then for the Cartan elements. No? And then you can again plot it here in the similar diagram. You can plot, but now there will be 3 points because the vector space is 3-dimensional. So you can only have 3 eigenstates, right? So there will be 3 points. Then we'll see how they are all related. I mean, somehow you can. Okay. So, no other question? Okay. So I'll see you tomorrow. Then.